You're seeing my screen?
Yes,
Arul, you have to allow me to
Yes.
share the screen.
Yes, yes,
Yes.
visible.
Yes, sir. You can please press it.
Okay. So the first thing is I'll show you about our code generator. So this is our hardware. This is something which you would have seen in our promotion post also. So this is our NXP-based S32K144 series hardware. You are able to see my screen?
Yeah, we were able to see the screen, sir. Can you keep that board closer to that camera? Actually, we were seeing the off of the board.
Yeah. So this one?
Yes, sir. Now it's good,
Clear?
sir. You can, yeah, yes, sir.
Yeah, give me 1 minute. I'll see whether I can place it a little bit higher. Visible now?
Yes, sir.
I'm not able to see. 1 second. Camera. Okay, you are able to see this, right? This board? Please reconfirm.
Yes, sir.
Yes, sir. Yes.
Perfect. Okay. So now this is the NXP S32K144 series microcontroller, which is an automotive grade ASIL B certified IC, which is used by most of the automotive designs. They use this IC. And this is ASIL B only. Some of the cases where you need ASIL D, they have their own controllers. NXP has their own controllers like 344 and other series. So in this example or in this board, whatever board we are promoting, this is the board which we have developed. And this contains the NXP S32K144 series. Okay, so, and this is the tool which is used to design. This is the IDE which we use to design the all the related, like the firmware design, configuration, everything is available with this S32 Design Studio. This is the IDE which is provided again by the NXP. So what we have done is we have designed a plugin on top of this NXP S32K, Design Studio. We have created a plugin called Smart Wheels. This is the plugin which sits on top of the same IDE and provides you an integrated platform again, so that the code generator can directly work on top of the IDE itself. So in a quick way, if I have to explain, normally if we sell this hardware to anybody, the first thing you are going to ask me is like, where is the schematic? Which are the pins? Like, which is the digital input? Which is the digital output? How is it connected? Is it internally pulled up, pulled down? So you are going to ask hundreds of these questions. And even if I give you this board today, to just make the board work, like maybe just to take a digital input and drive an LED. Assume that I want to read an digital pin. Say this is the switch. This switch, if I press this switch, an LED has to be switched on. Maybe the LED is here. So if I press the switch, the LED should switch on. If I have to make this, the first thing you'll do is you have to debounce. The switches are not, they are mechanical switches, so there will be noise on the switch. So you have to write the code for debouncing. Then you have to write the code for driving the LEDs. maybe it's a simple code, but you have to switch it on and off. Now, the second thing, assume that you want to read data from an ADC. So there is a potentiometer here. And if you want to read the potentiometer data, you have to enable the ADC. You have to start sampling the ADC. Normally, the ADC, if it is 12 bits, you have to just convert the data into 0 to 4095, it will convert. Then you have to filter the noise. So there will be a lot of noise in the ADC signal. Then you have to, normally we scale it up. We call them as mapping, or we call them as scaling. Like if the value is between 0 to 4095, this value, which is a 12-bit ADC means, that has to be converted to 0 to 100% means you have to write a code for that. 0 to 4095 converted to 0 to 100. So all this activity, you have to write code for that. And normally the example projects which are provided by any of these IDEs will be called blocking codes. Blocking code means it will do only one work. There will be a code for digital input, digital output, ADCs, PWMs, everything. They'll give you a code where only that will work. If you have start integrating everything, you will see that the one of the code blocks the other one. One of the code may have a delay, which is going to block the other one. So these are some of the typical challenges which we face when we write an embedded code, because timing becomes very critical. So what we have done is, with years of experience in this field and understanding AUTOSAR to a decent extent, I would say, we are working on AUTOSAR from quite long, but it's a huge topic to understand. And so what we have done is, we have completely built the BSW stack such that it can be used as a ICC1 compatible stack. AUTOSAR provides three layers. One is called ICC1, ICC2, and ICC3. Each one has got their own what you call rules to follow. ICC3 is the highest standard, where typically, currently, if you look at it, vector, EV traces, so these are the guys who are giving the complete stack on ICC3. But ICC3 stack is very, very heavy stack. So most of the edge ECUs, which are doing some simple work, like taking the accelerator data, controlling the windows, headlight control, backlight control, these are the ECUs which need not have a very full-fledged ICC stack or ICC3 stack. That is where the ICC1 stack comes into picture. And there are some rules. The rule number 1 is, it has to follow AUTOSAR standards in ASW layer, the application software layer. And rule number 2, it has to follow the RTE principle. That means any data exchanged between any two components, any two software components, has to come through RTE. The third rule is, it has to be a layered architecture. That is ASW, RTE, and BSW. Malay sir, can you just send me that PPT document in the meantime, maybe through mail?
You want that blink LED light?
Yeah, that one, and also the this one. We have the
block diagram
flow. Yeah,
the block diagram.
Yeah, block diagram. If you can just send me through mail also, I'll just take it. So in the meantime, so ASWC, RTE, BSW, and BSW is what is going to be generated by your EB traces, vector.
Narayan sir, it's on the AUTOSAR stack teams.
Okay, perfect. I'll just take it.
If you go little above, I can post it once again.
Yeah, please.
We just do it so that it's your last day.
Yeah.
I've done that here.
Yes, maybe the VFB also, please.
The VFB also, I'll give you that.
And so coming back, so we have the ASW, RTE, and BSW. So the BSW, according to ICC1 standard, can be a complete black box. That means you can write the code the way you want in the BSW layer and make all the peripherals work for you. But the application layer and the RTE layer has to follow the AUTOSAR principles. That is the rule. So the application layer and the RTE layer has to follow the AUTOSAR rules, but the BSW can be a complete black box and it need not follow any of the AUTOSAR standards written there. Like maybe it need not worry about the MCAL layers, it need not worry about RTAS. So there are many things which are, it's completely black box. You can write your own CAN stack, COM stack, Ethernet stack, IO stack, NVM stack, all these things can be your own stack. It need not be AUTOSAR standard. So that is the whole idea. So now what we did was, we started with building our own BSW stack. And that is the first demonstration I'm going to give you so that it becomes easy. When you buy this kit from us, one of the biggest advantage you are going to get is with AUTOSAR or without AUTOSAR, you can use this code generator for almost all applications. It need not be automotive. For any of the embedded applications, you can directly use this code generator and make your life easier in writing this code. So let me directly jump into the demonstration. So I'll come back to this and show this later when I need the RT. Okay, 1 second. Yeah. So when I Sir, you have the VFP diagram also?
I'm giving you the VFP as well.
Yeah, please. Sorry.
I've given you all the paths.
Yeah, perfect. Okay, just to give you a perspective, normally this way, the first topmost layer in AUTOSAR is called the application layer, or we call it as the ASWC, application software component layer. Then you have the RTE layer, and below this sits all your BSW layer, which is called the basic software layer, which will be auto-generated by any of the AUTOSAR compliant tool. The ASWC, even though it is auto-generated, but it has to follow some standards. It has to come through something called an ARXML file. Everything has to be generated through an ARXML file. That I will describe when I'm showing the demo first. So ASWC, RTE, these are should be AUTOSAR standard when we do the ICC1, and BSW can be a black box. So let me tell you what that black box means when I proceed through the demo. Now, I'll not go into AUTOSAR first. Normally, in an embedded system, even if you take a microcontroller and if you want to read a switch, debounce the switch properly, and if you want to drive an LED, that itself is a challenging job. If you are new to a controller and new to an ID development platform, that itself will be a challenging job. So let me show you how our code generator, along with the NXP tool, it's going to help this in the process. 1 second. Any idea how do I remove this from my top? Okay, I'll keep it here somewhere. Okay, fine. So the first thing I'll do is I'll create a sample project. Okay, so when you install this tool, we will give you a link from which you can install this plugin, which is called the Smart Wheels plugin. It will work along with this hardware. Okay, so now I'll create a new project from the template. I'll be a little quick. So definitely there are a lot of videos available we have created which can be used, because I want to cover the AUTOSAR part more today. So I'm going to take this. We have created multiple templates for different boards what we have. So this is our micro board, Smart Wheels micro board. So for that, I'm selecting that project as the template. So, and I'm going to create a project name. So I'll create it as test1. And so what this is going to do is it is going to use the template file which we have created, in which we have already specified all the required inputs and outputs of this device. So if you look at it, NXP provides something called a MEX file. If you click on this file, this is the file in which you can configure all the inputs and outputs of this device. This is a 100-pin device, but we are not using all the pins. So you can notice the port D, pin number 16, is connected to green LED. So there is a tricolor LED here. In the tricolor LED, the green LED is connected to port D. There is an I2C. So the I2C is connected to these two pins, PTA2 and PTA3. And the blue LED is connected to PTD0, a red LED is to PTD15, and the switch is connected to digital input, which is connected to PTC12. Okay, so these are some of the pins which are already connected, pre-connected in the board based on this. So it is ready to use. You don't have to worry now. So the second thing normally you do is you will configure the peripherals. If you look at it, if you want an ADC, the ADC has to be properly configured. You don't have to worry. This is pre-configured for you. It is ready to use. And it has got two ADCs. You can have multiple channels also. You can expand these things because all the pins are bought out. You can have multiple channels here. There are two ADCs. Both of them are configured. The CAN is configured. CAN is configured to work at 500 kbps. Okay. And you have the okay, so UART is also configured. You can use UART. As of now in this demo, I will not be showing. And there is a timer which is configured, which is used for all the timekeeping of for this application. Okay, so this is the LP timer, low power timer, which is configured for 1 millisecond. All the CAN messages, your input debouncing, blinking, everything is running through this base timer. And this is pre-configured for you. So now you have the pins are ready. You have the peripherals which are ready. The third thing we configure is normally the clocks. The clock is also completely configured for you. See, the FlexCAN is configured to work at 48 megahertz. So that is configured here. So you don't have to worry on configuring the clock, the pins, or the peripherals. Everything gets pre-configured for you because of the template project which we are providing. If at all you want to change, you can change. Assume that you don't want to run your CAN at 500 kbps. Instead, you want to run at say 250 kbps or 125 kbps. Come to the CAN and just change that parameter. Everything will remain same. You can just modify this and it will be working now. So once this is configured, let us go into the code. Normally what happens is in any project, if you configure all these things, you have to write the code. Or you have to take an example project or copy paste or do whatever you want to write, you have to write on your own. So what we have done is we have built in the Smart Wheels code generator, in which you just tell the Smart Wheels code generator what to do. It will automatically generate the code. So now let me just show you. So this is the ECUX file which is going to be created the moment you take this template. This ECUX file is generated from this Smart Wheels. So you just double click on this. It will tell you all the peripherals which are readily available in this particular board. If the board is different, the number of peripherals of IO will be shown differently. In this case, you have two switches and one tricolor LED. So RGB LED and one potentiometer is the analog channel. If at all you want to add, we are coming out with the next tool where you'll be able to add more peripherals also in this for your custom project. Now, what I'll do is I just select two digital inputs. I want two switches. Maybe I'll select only one switch and I'll select all the LEDs for the demonstration. And maybe I'll select the analog channel also. So if you look at this, it will allow you to configure these things, whether it is an active low, active high, and which one you want to detect, falling edge or raising edge, what should be the debounce. So all these things can be configured. In the same way for LED, In the same way for analog also. So you can set the interval, you can assign the mapping values. All these are readily available. You just have to select them. So as of now, I'll leave everything to default because default will work for most cases. So once this is done, now I told the system that these are the inputs and these are the outputs I'm going to use. One digital input, one analog input, and 3 digital outputs. These are digital outputs. So these are the things I'm going to use. So 1 second, how do I, sir, any idea how do I minimize this? Hide. Okay, done. Okay, fine. Now I'll go to application. I have selected what are the inputs and outputs I want for this project. The second thing I'll do is, what is the application? That means, let me just select one simple example the way I told. I'll create a runnable. Runnable, some of the terminologies we are using, what AUTOSAR uses, so that we are very clear in the terminology also. Runnable is nothing but a function which just executes. Whatever code you write within that function. That function is called a runnable. Okay, so I have created a runnable. In the runnable, you are going to add some input output. Yes, please.
Sir, where you take the application configuration block, sir?
Yeah, you have to just click on this. See, this is the IO configuration. If you
Where,
click on,
sorry, can you highlight it? One?
At the bottom, if you just see at the bottom,
in the
the
bottom.
tabs.
Oh, in the bottom. Okay. Yeah, continue, sir.
Yeah, this is the IO configuration. First, you select the IO. Next,
Okay.
you come to the application configuration
Yeah,
and
yes.
select the input and output. So in the input and output, I'm telling whenever the digital channel 1 is pressed, switch on the LED. But we have already told in the IO configuration that it has to be debounced properly with a 25 millisecond delay. So,
one thing, I have one question.
Yes,
For the MCAL layer,
Uh-huh.
MCAL layer, you are configuring via S32 platform.
correct.
And with EV, it is possible or not?
See, there are two parts. See, MCAL is required only when we do the ICC3 setup. In ICC1, you don't need to use MCAL. You can use your low-level drivers also.
Okay.
See, in NXP itself, in any microcontroller, if you look at it, they will see, first thing is you can directly operate on the pins by writing to registers. Correct? That is the first way.
Correct.
The second way is every company will give you a low level driver, or they will also call that as a HAL layer, hardware abstraction layer.
Correct.
Or as per the AUTOSAR standards, they don't tell hardware abstraction layer also. They call it as microcontroller abstraction layer, which is the MCAL layer. Here, we are not using the MCAL layer, but we are using something called the RTM layer, which is called a real-time module layer, which is similar to your HAL layer, hardware abstraction layer.
But Ashish, using this kit, right, you can configure the MCAL layer as well.
Yes.
That's correct, right? I mean,
That's
they
true.
can buy the kit and also learn how to configure the MCAL layer of this board as well.
Perfect. So the only thing is when you come here, instead of using this driver, what you have to do is when you click on this, it will give you, see now we have put the RTM library. When you select a project, see now you can use the MCAL layer also. This is the RTM library. The same thing you will get it as RTD library, real-time drivers library from NXP, which will assist you in configuring the MCAL layer with the same board.
Okay. But one thing I just want to know that the same thing what we are doing via S32 platform, the same thing we can do with a EV also. Or
you can do that with EB as well, Ashish.
Yes.
Okay. Actually, I'm also in AUTOSAR course from your institute only.
Right.
So
you can do it with the EB resource as well.
Okay. Okay.
I'll
Fine.
just explain that how we take the data from, we call that as an ARXML file. Everything happens through ARXMLs. So
Okay.
you can
Okay.
take the ARXML file and import it here into our tool, the GenX tool, or you can import it into vector, or you can import it into EBIT resource, the same ARXML.
Okay.
So that
Okay.
is the definition of AUTOSAR, where it should be cross-platform compatible.
Yeah. Correct only.
Okay. So now
Okay.
that we
Thank
have config, yeah, perfect. Good question, sir. Good question. Yeah. So now what I have done in the application is, see, I have selected the IO. I have selected these IOs. One of the IO I am mapping it, digital input channel 1. When it is pressed, the red LED should be on. That's what I am telling. Now, this code has to be written in this function. That is called the runnable function. Now what I'm going to do is, I'm going to tell in the scheduler when this function should be run. When is this function going to run? So for that, I'll create a scheduler task. So I'll just say every 5 milliseconds, just run this function or the runnable. I'm just mapping this runnable to a scheduler which is going to run a task every 5 milliseconds. In the runnable, it is going to read the status of the digital input, and if it is pressed, it is going to switch on the LED. If not, it is going to switch off the LED. That is how it is mapped. This is a simple example to start with. Now, what I'll do is, I have done my configuration. I have to generate the code. So for that, come here and click on, either you can click here, say generate. So I'm on a trial period license. So now it is showing the directory. When you say finish, it is going to generate the code. So it has generated all the codes, how to read the ADC, the state missions, everything it has generated, and the code will be ready to use. So now what I'm going to do is, this is going to be in this particular generated folder. I'm going to copy paste this into my source folder, because this is not going to be compiled. This is the source folder. If at all you want to make any edits, you can edit it, so that the generated folder and the source folder will be always different, so that it won't overwrite until unless you do it. So now I'll just format it and I'll just show you how the code is generated. So if you look at the digital inputs, so we selected one digital input, and that digital input is configured here. And we have generated the digital outputs, which we selected 3 digital outputs, 1, 2, 3. And the pins, everything is configured here based on whatever you selected on the tool. So it has generated the code for that, and it has written the function also. So the functions will be like DO, digital output, LED red, set value, and you give a value, and it will automatically call the function, and it will write the low level drivers and make sure that the pin is on. This is the function you call for setting the red LED. This is the function you call for toggling the red LED. So read, invert, write is toggling. So that will be taken care by this. This for the green LED, and this is for the blue LED. For each of the LEDs you have selected, it will write the functions based on the selection here. And once this code is generated, now I'll not do anything. I'll just show you the code. And if you look at the scheduler also, there is one function which is going to run every 5 milliseconds. And when this function runs, it is going to execute this runnable. Where is it called from? This is going to be called from the scheduler. This is the task. This is the 5 millisecond task, will be run every 5 milliseconds. And from this, it is going to call this R1. That's what you configured. Based on that, it has written the code. Once the code is written, now you are just going to compile this. Okay. So now once it is compiled, I'm going to download it. So this is the project test one. So I'm going to download it. So the debugger is inbuilt. Okay, so you don't need anything, just connect an USB cable and it will start working. It's an isolated debugger. So you can directly connect it to your PC or laptop and start working. So when I run this code, so the idea is when I press this switch, you can see the red LED glowing. Note that the switch is properly debounced and all those things are taken care by the functions. Okay, the scheduler will call the task. The task will in turn call each of the inputs and output. So all those things are managed, and you will get a complete library file which is going to completely call those things and ensure that your system is going to work. Okay, this is on the Gen X part. Now what we did was we have read the digital switch and you are driving the LED. Okay, that is the example we have created. You may ask, like, where is the ADC? Where is the data for ADC? So for that, what I'll do is I'll just add the CAN also so that it is very clear for you how easy it is to send a CAN message from this system. So what I'll do is I'll go back to the ECUX editor. This is our Smart Wheels editor. Come back to the TX configuration. This is the CAN TX configuration. Now, you know that in automotive, we don't send direct CAN messages. The CAN messages are always going to come from a DBC file. So the database configuration file or the DBC file. So that is the file through which you are going to sell. The DBC file will contain, it will contain everything. It will contain the type of message. It will contain what frequency the message has to go, which are the signals in the message, which is the position of the signal, what is the type of signal, minimum value, maximum value, everything will be mentioned in the DBC file. So I'm going to demonstrate that directly DBC file itself. So what I'll do is I'll select a typical DBC file. It is in this folder. I'm going to add a DBC file. You can take any DBC file, whichever is yours. Then in the DBC file, if I say add message from DBC, means it is showing all the list of messages which can be transmitted from this node. I'm going to select these two just for the demonstration purpose. The moment I selected that, it is showing all the signals related to the message, and the message ID is 64 hex, which is 100 numeric or decimal, and it has to be transmitted every 50 milliseconds. And this engine status is another message. 65 is the code, and this has to be transmitted every 2 milliseconds. So I have just selected two messages from the DBC file. So now what I'm going to map is, now I'll just, when the switch is pressed, I can directly tell that send it onto the message. So that from the IO configuration, from this digital one channel, what I'm telling is, if the switch is pressed, this message is going to go every 50 milliseconds. And if it is pressed, send the status of the switch in this particular signal. There's a 1-bit signal. In that you send it. The same way, in the engine power or engine force, whichever you want, because it's a 16-bit value, I'm just selecting the input and selecting analog channel 1. So when I do this, your ADC data will be sent through a CAN message 64 and through a signal called engine force. Sorry, engine power. This is where we are sending this data. So now the code generator will write all the required code for properly packing. This is an 8-byte message. Okay, this is an 8-byte message which is going to go. This is a 1-byte message, and in the 8 bytes it has to properly pack the signals based on the position, and all those things will be taken care by the code generator. So let me just save this and generate the code. Yeah, I finished it. Now the code is generated. If you look at it, it would have generated powertrain based on the DBC. This is the file it has generated. Packing, unpacking, all the functions, left shift, right shift, checking for minimum, maximum, all these things will be taken care by the code generator. Now, what I'll do is I'll completely copy paste this to the source. look at it, this is your has written this function, and based on the, see, this is the function which is going to send the data, and this, it is going to read the ADC data, ADC analog channel 1 get stable value. It will do all the filtering and everything. It will take the data and put it onto the engine power encoded value. Engine power is the signal in which you wanted to transmit the data. So that one, it is properly putting it across. The same way, switch status, it is transmitting it on this particular signal. So once this is done, it has properly written the code. So it will just, now let me generate the code now. So this is compiling now. The code is compiled. Then I'm going to download. The idea is, when I transmit this message, I have connected a hardware. This also hardware comes along with the kit. Whatever kit we are promoting now, we want to give you an entire infrastructure so that the day you get this, you should be able to start sending a CAN message. So we will give you this, we'll give you this hardware, the cable, and you have a software called TS Master. This is the software which you can download, and it works with this hardware. This TOSUN hardware, the TS Master works. So in this case, once you open this tool, I'm going a little faster so that I can cover whatever possible today. So once you open the TS Master, you'll be able to see all the messages. Whatever message you want to see, you'll be able to see it here in the trace window. Okay, so I'm going to start this. I've already pre-selected it. I'm going to start it. And if at all a message is transmitted by this hardware through the CAN wires, this will receive through USB. It is going to send it across. Okay, so let me start this. It is started. Now I'm going to run this, and you can see the messages coming here. One thing what I have done is I have added the same database here also and kept it ready so that all the messages, whatever you are receiving, it is properly unparsed also at this end. Now, if you look at it, it is sending the message every 50 millisecond. If you look at it, this is coming every 50 millisecond. This message is coming every 2 millisecond. Every 0.002, 0.050. Accurately, it is transmitting the data every 50 millisecond. And this one is transmitting data every 2 millisecond. Now, look at this. Engine power is the one which we have connected it to the ADC, which is connected to the potentiometer. Now, if I move the potentiometer, you can see the value changing here. So you are able to notice it, right? In the same way, if I press the switch, you can notice this. This is idle and this is running. If it is 0, if the data is 0, it is running. If I press this button, it becomes idle and this becomes 1. Okay, so this is for transmitting of message. So in the same way, the reception will also work. Due to paucity of time, I'll directly go to AUTOSAR and try to demonstrate. If you have any questions till now, please let me know. I'll go to AUTOSAR demonstration directly.
So guys, just to keep you informed, in our kit, you will also get the TOSUN hardware along with the board. So you will be able to use the TOSUN TS Master software for all your simulation work as well.
Sir, actually, configurations, it's given a default to driver size, sir, or we can do configuration based on the requirement.
Can you repeat the questions, please?
The IO configuration like ADC, DIO port. Okay, these are the modules we have a configured based on the requirement, or default the drivers are given.
See, default drivers are given. If at all you want to make changes, you can make changes. Assume that you have a switch which is not digital input switch is not falling edge. You want to make it as a rising edge you want to detect. So you can come and change it here.
You can change it in the code generator or here in the code as well.
In the code also you can change. You want the debounce to be 50 millisecond, you just change it to 50 millisecond, it will change to 50 millisecond.
Okay, we change the 50 millisecond and build it and download.
Build it and download. You want to change the pin. If you want to change the pin, see, this is where if you change the pin, you have to come and change the pin configuration in the tool here.
But actually, we don't have an experience in driver side, sir. If you provide any information for this one, any videos, like any for driver side.
See, that we can definitely support. See, if you can let us know which is the hardware, how is the hardware config? See, currently our code generator is directly mapped to our boards. We have 3 or 4 boards which we have released. For each of the boards, we have a template file. Assume that you want to use this code generator for your board. We will always give you a support. That will be a separate activity. We will take it as a like service activity and create a template file for you. And we will configure the code generator also for that. So that the entire code is generated for you. That will be a separate activity. So any other questions? Do you find this useful? Where it automatically generates the code. Now, the other thing is if you want to write your own logic, using these functions, you can write your own logic and your own functions also. It doesn't restrict you. Assume that I want to create a new file and start using the debound status. Use the debound status. If the switch is pressed, this is the function you are going to call. This will tell you 1 or 0. If this is done, then what you want to do is up to you. Or you want to detect, see, this is the function which is going to be automatically generated. Is edge detected? It will give you a function. You call this function, immediately it will tell you whether the edge was detected or not. Just check that function and write your code. So all these things can be done. Even for ADC, it will give you all the functions. Get raw value, get filtered value, mapped value, stable value, or your own algorithm. If you want to write, you can write everything here. So it will give you all the functions which are required for typical use case of any microcontroller. If you are using for designing anything, robotic application, medical application, industrial application, for everything you can use this standard because there is no AUTOSAR in this actually. So now let me come to the AUTOSAR part. So in AUTOSAR, it is not straightforward. So in AUTOSAR, everything is split into layers. That is, we have the ASWC layer, as I described, ASWC, then the RTE, then the BSW. Here, everything is working as a single layer. If you look at it, the current code generator. But in AUTOSAR, it describes that you have to keep all your application logic in a separate .c.h files. And for that, you have to create an ARXML, or the ARXML has to create the .c.x file. And you have to create the RTE file. The data exchange between BSW and ASW should happen only through RTE. That is the rule. And if one software component has to send data to another software component, then also it can't directly transfer. It has to go through the RTE only. So that is what the rule says. So now this becomes little complex for any good embedded engineer also. So any good embedded engineer who may have like 10-15 years experience in embedded, if he comes to AUTOSAR, definitely he's going to struggle because the architecture in which AUTOSAR has to be designed is different. The first thing we have to do is create a proper VFD diagram. This is called a VFB diagram. That is virtual function bus, in which we will mention which are the different software components we have. When we say software components, in this case, I'll tell you, just reading a data from a switch is a separate software. Controlling an LED is a separate software. And putting your application logic, it's a separate software. When I say logic, This will read the data. It will only read the data. It doesn't know what to do next. It will give you the data. That's it. That is the switch data. This will only write it to the LED. It doesn't know where the data is going to come from. The application software is the one which is going to take the data from this and put it here. That is when the switch is pressed, switch on LED. That is the application logic. That is going to be written here. So if this is the flow which has to be taken care, to write this, you cannot directly write. You have to follow lots and lots of standards which the AUTOSAR specifies. The first thing is we call them as interface. So you have to create interfaces, then you have to create ports, and you have to properly tell whether it's a client port, sender port, receiver port, sender receiver interface, client server interface. All these things you have to study. Trust me, it's not straightforward, little tricky. But if you go through the proper training process, definitely you can understand. But it's a big document out there. So now you have to create a proper ARXML file, AUTOSAR defined XML file. So that file has to be created for this activity. From this activity, you are going to tell how it is going to be connected to the RTE. From the RTE, how it is going to be connected to the BSW layer. So this will be done by a separate team. This will be configured by a separate team. Note that in AUTOSAR, nobody writes BSW layer. It's only configured and auto-generated. Here, 80% of the code is going to be generated based on the ARXML. You are going to only write the application logic inside these software components. Every port and every interface, the function names, the parameters you are going to pass, whether it's a pointer based, reference based, value based, all those things has to be pre-configured in the ARXML file. No code. You cannot directly write code. The tool has to generate the code, and the file, the .c, .h files has to be generated. In that, you have to go and do the fill in the blanks only. So with that little understanding, let me just directly go to the ARXML tool generator. Okay. So what I'll do is, okay, first thing is, let me clear these things. Okay, so there is a tool called RTOP. This is the tool which normally people use to create the ARXML file. Trust me, it's very difficult. Okay, otherwise Vector gives you a tool called Ancit, which is easier, but it is exorbitantly expensive. So most companies use RTOP as their one of the ARXML configurator tool for application. So in this, what we are trying to do is, we are going to give you one more software which is called the Smart Wheels AR. This is Smart Wheels, whichever the plugin which is going to get into NXP, which is going to generate your BSW layer, is called Smart Wheels. And the Smart Wheels AR is the one which is going to give you the configuration tool for your ASW. Okay, so let me start with a new project. I'll get the folder. Sir, this has to be changed to folder name, sir. Malay, sir. Next time. So I'll use this folder just to sake of. I'm going to create in this folder, and I'm going to give a name. It's called Smart Wheels V1. It is going to generate the ARX file. Note, before that, I will tell you the process. How the AUTOSAR, we call that as a methodology, and how the AUTOSAR methodology just works. Quickly, I'll tell you. The first thing you have to do is, you have to use a tool which is going to generate an ARXML file. because AUTOSAR works only with ARXML files. Whether it is ASW or BSW, it needs ARXML files. So now we are going to use the Smart Wheels AR, which is actually going to generate a file called ARX. This is our own file, Ancit's file. From this ARX file, we are going to generate the ARXML. From the ARXML, we are going to generate the .c and .h. This is only for the application layer. Okay, so take the Smart Wheels AR, configure whatever you want. It will generate a .arxl file. Then from there, it will automatically generate the ARXML file, which is a very difficult part. Once that is generated, then again it has to generate the .c and .h file, and that will also be done by the complete Smart Wheels AR tool, which is again AUTOSAR ICC1 Stack compatible. From this, whatever ARXML is generated, you don't have to generate the .c .h. You can directly take the ARXML to EB Trezor or Vector Davinci and then generate your .c and .h files. The same ARXML can be used. So let us start with this. First, let us create that ARX file. So this is going to create that ARX file. In this ARX file, you are going to tell, in any embedded system, there is input, there is output. Inputs are called sensors, outputs are called actuators. And you have an application logic. Only three things: input, process, output. That's it. That is an embedded system for you. Whether it is AUTOSAR, non-AUTOSAR, anything you take, that's what it is. Your whole logic depends on these things. So what I'll do is, in this example, again, I'm going to create a simple example wherein I'm going to create one sensor and one actuator. Sensor is my digital input switch. So I'll name it as digital channel 1. And my actuator is my LED. The same example I'll show you with AUTOSAR now. So digital channel 1 is the sensor, which is going to be read every 5 milliseconds. We have configured it, pre-configured. This can be changed later. Then you have the red LED. Once this is done, now this is going to, now you have to map this. Digital channel 1 has to be mapped to the red LED. So that we will do it in an application. So in this application, what we are going to do is, we are going to add a runnable in which I am going to map the channel 1 output, input, output, whatever I have selected will be listed here from the previous configuration. So I'm going to map this, and it is already going to give a name, proper name it is going to give. I'll just say okay. So now what this has done is, it is going to create a runnable. In this runnable, it is going to read from this and write onto this, but in AUTOSAR standards. Okay. So once this is done, I'm going to scan this one. Alt Shift H. Okay. No. Okay. So now I have mapped it. Now let us first generate the ARXML file. Okay. So now I have configured the ARX file. I'll save this file and I will generate the ARXML file. So I'll just say this. I'll generate the ARXML in the same folder. So when I click on this, so it has generated the ARXML file. See, if you are aware of how the ARXML file will be, see, look at this. If, one second, let me open this window and show you this file. Now, as I told you, this is my ASWC. This is the RT. Now you require an interface. If you want to read the data, you need an interface. This is called the client server interface. If it is like this, this will be the client server interface. And this is also a client server interface. So you have to create one client server interface. And this one is called a sender receiver interface. So you need a sender receiver interface for this application software component. This is an application software component which is called a sensor actuator application software component. These are unfortunately some complex names in AUTOSAR. This is a sensor actuator application software component. This is also a sensor actuator software application software component, and this will be your application software, ASWC. So this is some ports, some interfaces, some data types. All these things have to be properly configured in AUTOSAR, but those things, if you look at it, it would have pre-configured for you. So data types, whether it is input, output, which is the operation it has to do, all these things will be configured just by configuring. I just want to read from a digital switch. I want to write it onto an LED. And if you say this is application, the rest of the things will be auto written by our code generator or the ARXML generator. And it has generated all the implementation. It has created the composition. It has created interfaces. It has created ports. All those things will be coming within this itself.
In between, we have 412.
And if you buy our kit, we'll be giving you tutorials that will explain in detail these ARXML components and how they will be manually created as well. You know, we don't have the time to talk about it right now in the demo, but then you will get documentation on what are these each elements that is there inside the ARX.
Yes. Trust me, understanding this and creating this with the RTOP tool. If you look at it, see if I refresh it, it would have come in the same folder. See, if you look at it, you can open this in RTOP. And if you click on this, it will tell you what are the parameters it has configured. The same thing can be opened in RTOP. See, this is the get raw value. This is the operation. And this is the value. It's an output direction. And this is the value. And data type, implementation data type, it has already taken as a single bit value because it's a digital channel. If it is analog, it would have taken a 16-bit value. Because it is digital, it has taken a single bit value. So all these things are, again, you can directly open in RTOP and see how it is configured. The ports, the resources, everything are available here. Look at this. These are the software components. So this is your digital channel 1. In this, there is one client port. If you look at it, how do you refer this means? See, this is a client port. Look at this. This is a client port. This is a sender port. These two ports are created in this. One sender port and one client port. This reads the data. This is the one which is going to read the data and put it onto RT. As mentioned, RT is the boss in AUTOSAR. All data has to move between any two software components only through RT. So if this guy reads something, it has to put it back to RT. If this guy wants something, it has to read from RTE, process the data, and put it back to RTE. If this application software needs a value, it has to read from RTE and then put it onto other IO abstraction and other things to send it to BSW, wherever it is. So all these things has to follow through. So now if you look at it, it has sent all this, it has created the ports, interfaces. See, look at this. This has created a 2 client server interface, 2 sender receiver ports. So this is a client server interface. This is another client server interface. This is a sender receiver interface, and this is another sender receiver interface. So all the 4 have been created. So once this is created, now the ARXML job is done. So if I come back, open this, the ARXML is generated. The ARX generated the ARXML. Now we have to generate the .c.h file. Now directly this can be taken to EBtraces. Okay, the same file can be taken to EBtraces. Yes, please.
Sorry, sir. Actually, whatever your demonstration, that is already you have done for the all configuration in that sender receiver client server selections, correct?
Yes, I have selected it in here.
Already default before you selected, it's not showing now actually. Just you are showing only how to do it only, correct?
Which one here? In this?
Server, client server, sender receiver. To see when you are create any component in ASW, okay, we have selected that is what is the type of component, like application component or
Okay.
like
Okay,
sensor.
we have changed the way. That's a very good question. Normally, when you approach AUTOSAR, right, your
correct.
approach is to create all the interfaces yourself, to create all the ports yourself,
Correct.
then like all the data types yourself.
Correct. Basically,
But that is
developer
a
will
painful
have,
job, right?
yeah, developer, we can do these kind of things actually.
Correct, correct. So what we did was, we said, okay, let us not worry about those things. Embedded is all about input, process, output. Correct, right? You take any microcontroller application.
Correct.
So we changed the way we are looking at things. In fact, even it was very confusing for me when I moved into AUTOSAR. Okay, why should I configure all these things when I know my simple work is input, process, output? Whether it is with AUTOSAR or without AUTOSAR. Do you agree with me?
Yes, sir. Correct.
And
Yeah,
in input, you have only digital input, analog input.
Mhm.
Maybe frequency input also. Frequencies also can be considered as analog only.
Yeah, correct. Yeah.
Now, in the output, if you take, you have analog output and digital output. If you take outputs, either you are going to drive a PWM. PWM is an analog output if you look at it.
Yeah.
But if you take a digital output, it is 1 and 0.
Hmm.
So now, if you can distribute these things to simple input, process, output, and if I can generate my 80% of the ARXML, and wherever modification is required, I'll only modify that.
Hmm.
So what this does is, it gives you a very, see, a new person coming into AUTOSAR, if I ask them to create an interface, ask them to create a port, then data types, implementation data type, application data type, they will go nuts. Agree?
Yes.
So what we want to do is, we want them to first understand what we are trying to do and how the ARXML is mapped. See, as I told you, if I give you a VFB diagram now, if I can give you a small training on how to look at a VFB. One second, let me just, okay, this is your VFB. Simple VFB, correct?
Hmm.
In this VFB, I'm telling that there are two interfaces. This is a client server interface. And this is what I have to create first. Okay. And if I go back and show you here, this is how it has been created. See, look at this. It has created. First thing is, it created a software component. See, you have to create a software component first.
Hmm.
There are three software components. One is sensor software component for reading the sensor. Then for application logic, you have an application software component. Then for an actuator, we have an actuator or sensor actuator software component, which is going to drive the LED. All three are separate software components. You have to create three application software components. That is the first thing when I look at this VFB. Correct?
Hmm.
Now, see, this is what I have created. Sensor software component.
First package on the top.
Yeah, sorry. If you look at it, software components. So I will go to this one itself. Better is to show it here. Yeah. See, I have created the sensor software component, the actuator software component, then the application software component. These are the three which I have created. For that, you have to name it properly, but we have already named it based on the sensor name you give. You give a different name, it will create a different name sensor component. Digital channel 2 means it will create channel 2. Channel 3 means channel 3. Instead of digital channel, you want to make it as a switch 1. It will create switch 1.
Okay, sir. But I want to one more component creation. It is possible, sir. We can create.
Yeah, very much. See, this is going to be your ARXML file. Whichever you want to edit, you can come and edit it here.
Okay.
So we are giving you a generator along with an editor. So you can edit the ARXML. But what we are saying is, why start from scratch? We'll give you the basic ARXML.
See, again, very few people have the luxury of working with Vector Davinci.
Correct.
Very few, handful.
We are using regularly Ancit developer and configurator, sir. That's the reason I doubt about that.
You are lucky.
Like because of their Ancit developer, we want to create the own component also, like application software component or
Sir, if you
actuator.
go to our software, na, if you go
Yeah.
to Smart Wheels AR,
Yeah.
1 second.
and go to the software components. No, sir, go to ARXML, select 01 software component.
Okay. Right click on.
Right click and we will allow you to create. Sir, show right click. No, sir, 01. Huh? We are enabling all this. So very soon you will have a complete ARXML editor. And we are also doing a 2D based editor like DaVinci. So you'll be able to drag and drop and connect them and you will get the ARXML.
Mm.
So that will be, so anybody who's buying the stack and the tool from us this year, he will keep getting free updates through the year as we keep improvising the tool.
Okay. Okay. Okay, sir. Yes, we can continue.
Okay. So thanks, Malay. And so, so we have created the ARXML now. And ARXML contains, based on the VFB, it contains all the parameters which are to be configured. So then the next thing is, let me go back to my, I have to generate the RTE.c and .h file. All the ASWC, whatever I have created now, 3 software components, basically 4. There is IO abstraction also. For all these things, I have to create the .c and .h files. Again, you are not supposed to type it. It has to come from the ARXML file. Okay. So how our tool does it is, you can come here, click on this. See, this you created for generation of ARXML. When I click on this button, it is going to ask for the ARXML location. I'm going to give the ARXML location. And now let us hold here. Now this is going to generate some files, .c .files. Where should I put it? So for that, what we'll do is we'll create a template project. We need to integrate the ASWC with the BSWC. So we are going to use this GenX tool for that. Okay, so what I'll do is I'll create a new template project, same the way I created previously. Whether it is with AUTOSAR or without AUTOSAR, the process is same for us. So select the library file. Then I'll give you this, we'll call it as test2 or AR10. I'll make it as AR10. Finish. Okay, so I'll put this into debug flash. So now the first thing is I'll build this project so that I'll check whether everything is proper. The base configuration, nothing is here now. The first thing I have to bring is the ASWC. Okay, so the ASWC is not here. It is going to be generated by this tool. So what I'm going to do is I'm going to take this folder and tell you generate the ASWC into this folder. Okay, I'm going to use this folder. There's a new project which I created. I'm going to give this location. So take the ARXML file, which I created from this, and put it onto this new project which I created in this ASWC folder. You put it across. So when I do this and say finish, so this is going to generate using this ARXML file. It will write all the codes, required codes. Just refresh it once. So it has generated all the codes. So look at this. This has created the digital channel 1 code. This is your IO abstraction code. This is your application code. And this is your actuator code. So now this is your ASWC and this is your RT, the complete RT. Okay, so there are some minor bugs in the tool which we are fixing it out. So now it has generated the ASWC. Let us just build this and see whether it is going to build. So it is giving some warnings. These warnings are like unused. Some of the functions I have not used. These are because it is connected to this one, the BSW layer. So that is why it is calling it as unused. So we will not worry about it. Warning we'll ignore. Now note, I have bought in the ASWC. So if you look at the code again, I have got the, yeah. So if you look at this VFB, I'm telling this part of code is generated and the RTE code is generated. The RTE.h and RTE.c is generated. This is generated. Now we have to generate the BSW code. Okay. So the BSW is going to be generated by this tool. Either it will be EBTresors, Vector, or our GenX tool. That is the one which is going to generate the BSW layer. So I'll click on this. The first thing I'm going to do is I'm going to open this ECUX file. Not that, sorry. First, I'll close all these files. Too many files open. The way you exported here, you have exported from here the .c and .h files. Here we are going to import those things. So you can just click on this particular item and just point the ARXML file. This also requires the ARXML file. So I'm going to use the same folder. This is the folder I created the ARXML. So this is the ARXML which got created at 6 o'clock now. So just say finish. The moment I press that, now it has imported the ARXML file, and based on that, note whatever configuration you made, based on that, it has properly configured the peripherals also. So TX will do it later. So it has configured the peripherals and it has kept it ready. So due to paucity of time, I'll just run little faster. Now I'll directly generate the code. I'll click on this button. Now this will generate the code. So it has generated the BSW code. So what I'll do, I'll copy paste this to the source as we did previously. And I will build again. The reason being, I want to know whether the BSW is proper. Okay, there is one bug. So this one, the runnables are not there. This next fix, we'll fix it in the next release. Yeah, this one also, actually, I have to include RT.h. Because the scheduler is calling that function, so I have to include that. So if you look at it, there are no issues.
So we can do that. That's it.
Yeah. So if you look at it, it is ASWC is built separately. BSW, this is your BSW stack. This is separate. ASW is separate. BSW is separate. Now we are going to link these two. Okay. So this linking is what in any AUTOSAR, whether you use EBTresors, Vector, anywhere, you are the one who is going to go and edit the code. As an application engineer, as an ASWC engineer, you are going to edit the code. Okay. So if you look at this code, this will be read by this port. If you look at it, I'll first open this. You are going to read from this client port and send the data to RTE through a sender port. Read through client port, send it through sender port. How do we do it? Is look at this. It would have created all the templates here. I'll open the sensor digital channel 1. See this value. See, this is the function which is going to, this is again all as per AUTOSAR standards. The name of the functions, everything will be taken, like whether the way it generates in EBTresors or Vector, that's the way it is going to generate. So this is the one which is going to read the data from the switch, and it will be stored in this, because look at this, this is a pointer. So this pointer will contain the digital switch status. It will read the data and it is going to write. It is going, this is the sender port which is going to send to the RT. So this is what we do. This is the code which has to be written by any application engineer working on ASWC. Okay. So read the data, which is going to be here. This is the where data will be there. This will be set to this value. This is the value which is going to be sent to this parameter or the RTE. And in the same way, we are going to do it for LED also. LED, what it is doing is, it is going to read from the RTE and write to the client port. Read and write. So this is going to be the read port. Okay, this is the receiver port. And this is the write port. This is the call function, or we call it as client port. This is the client operation, client writer. It's client. So it will take this data and it is going to set it to the LED value and it is going to send it to this. So now we have done this part. We have done this part. We have to do this application part. What is the application part does? When the switch is pressed, note that whatever is the switch value, it will come here. This is the application logic. This will read the switch value and it can assign it to the LED. Or you can write your own logic. You can invert it. You can do whatever logic you want to write, you can write it here. If it is pressed, if it is waiting for 5 seconds, after that you want to assign, all the logic can be done here. Okay, so for that you have to open this file, application file. It has already created all the ports. Look at this, it has got a receiver port and a sender port. This is a receiver port and this is a sender port, sender. Okay, this is the sender. So again, I'm going to read this data and write onto this. If I do this, it has taken the data and written onto the RTE. Read from RTE, write to RTE. Note, that's how this works. Read from client, write to RTE. Read from RTE, write to RTE. Read from RTE, write to client. So that is the process it has done. Now, this is done. Now you have to write the IO abstraction. See, till now we are only dealing with the application. Now in the IO abstraction layer, you have to use all the low level libraries or the mcal functions has to be called from the IO abstraction layer. And that is what is going to be done here now. So this is your runnable, which is going to be called by the RTE. And here you are going to map this. Read debounced status. No, sorry, not here, it's here. So this is again has to be written by an application engineer only who takes care of the ASWC. So this is the function which is driven again by the application ASWC interface or application interface, we call it as. So it is going to read the debound status and assign is going to assign to the pointer. Now for writing, it's going to use this function. Normally, if it is an AUTOSAR ICC3 standard, the function you will be writing is DIO write. Hope some of you can map this. Instead, because we are using ICC1 stack, it is our own function. It need not follow this function. This will be DIO write channel. This will be DIO read channel. If it is AUTOSAR ICC3. Because we are not using ICC3, we are using our own functions, which is going to be this functions. So now once this is done, it is going to set the value. This is going to read the switch value. So now this is done. I'll save all the functions.
Sir, that read we can give the end operator for IO
Read,
driver.
Yeah, one second. You are talking about
IO,
this one, right?
Yeah,
IO abstraction.
Yeah. Value LED read.
Yeah. So you can directly point it and write it.
Okay. Okay. You are directly pointed. Okay.
Yeah, I am directly pointing it and writing.
Yeah, yeah, okay, sir.
Hmm?
Yeah.
Perfect. So then, yeah, very good point you noticed, by the way. Thank you. Okay. So I'm going to now generate the code. Let me look into some warnings. That is, warning is because it is telling these two functions are not identified. You have to include those BSW header files. Genx di, these functions are here. Genx di.h, include Genx do.h. In your case, if it was AUTOSAR standard 3, it would have been include do. do.h. Here we are using di and do separate functions. So once it is generated now, so I don't see a problem. All are fully generated. Now let us download the same project. See, look how complex it is to build an AUTOSAR project. So that is why you need a lot of tools. So directly you cannot do it. So I'm going to download this. Not this, sorry. This is the old project. I will not download this. Stop it because it's a separate project. This project I have to download. And create this new project. Yeah, AR10 download. So if I run this, the idea is if I press this button, LED should glow. The LED is not glowing. Okay, that is because in the whole of the AUTOSAR runs on RTE, and I have to start the RTE loop. Okay, and that you have to map it again to the BSW. That is one more activity which you have to do. In any code, you have to make sure that that is done. So I'm going to call the RTE loop the end. So once I call the RTE loop, I have to include the RTE in the main. So I'll download this.
Sir, is it this RT loop what we are trying to invoke is the RT start function to initialize the software components?
The RT start would have been done. In this case, we are using our own see, RT start is not there. It's just a template.
Okay.
But see, RT will have two things. One is init and RT main will be there. Or
Yeah.
RT loop.
Okay.
RT main is one-time activity. RT loop is going to be continuously called. So if I show you the function, so this is the function. The RT loop functions takes care of all the events. Every 5 millisecond, we have told that every 5 millisecond, you have to read the input and write it onto RT. We have configured in the application, right? So if you look at it.
The task time is a 5 millisecond.
Yeah, 5 millisecond, right? So that will be taken care by this loop.
Okay,
So
okay. And is it can be also handled equally? I don't know. I'm not sure. Like RT start also can do that job, or
yes. RT start also it can do.
Okay.
As of now, we have not implemented it, but definitely we are going to implement those things.
Okay, sure.
So if you look at this code, 1 second, I'll show you this scheduler. The scheduler would have been rewritten in such a way that it is going to set the timing event.
This is the runnable which we are talking about.
Yes, this is the time. This will set the timing event. It will just set the timing event. The timing has happened because it is not running on OS. It is setting the timing event.
Okay.
But once the timing event happens, now this timing, when does this come into picture is this 5 millisecond is based on the task.
Because
every
this is
5 millisecond, this function will come and it will set this flag. Now the RTE loop is running. When this event runs, then it is going to call this function. What is that function? That RTE read is going to happen. This function it is going to call.
So that we get the data.
Yeah, which will take the data. This is the function which is going to be called. This function will be called. which is going to read the data and write onto RT. See, this is reading the data and writing onto RT. RT sender. And once this happens, right, automatically the rest of the events will also get triggered. You don't have to worry. Have you mentioned when should this run? You have not mentioned when this should run, because that is how the AUTOSAR works. When there is a sender and if it is mapped to a receiver, when this sends the data, this should automatically run. And when this sender sends the data, there is a receiver, this should automatically run.
This is since it is event triggered. What we are talking.
All these things becomes event triggered now. And look at this RTE. So that is how the RTE events gets set. Once the read channel happens, it will set the next event. Application data received event, which will actually call this function. Actually, if you look at it, this will call this function, which is going to, this function is going to just take this data and put it here. Okay, so look at this main function. Okay, this one, runnable digital channel to red LED. This is the runnable. Where did you configure this runnable? If you come back here,
inside the scheduler upload task, we have configured.
Yes,
given
so
the reference.
Correct. You have created the reference, right? Sorry, 1 second. You created the reference here. You created the reference in the application. This is the runnable, which is mapping the digital channel 1 to red LED.
Yeah.
And
that input is like our sensor and actuate output will be
output is an actuator.
Yeah.
So once this is done, it has written the code, and you also updated the code also, right? Your application logic also you wrote. It is directly, because it can have multiple inputs and multiple output also, the same runnable.
Actually, what you need in your application, based on that you have to adapt it.
Exactly. So once this is done, now I'm going to download. So I called the RTE loop. So if I run this and press the button, you can see the LED glowing. Finally in AUTOSAR. Yeah. So to make an LED glow with a switch in AUTOSAR, trust me, is a 1-month project if you don't know how to configure it. Do you agree with me, people who have worked?
Yeah,
If you're doing from scratch.
Yes. You are doing from scratch. You have to properly see, if it is MCAL, you have to configure the entire MCAL, right? Port, DO, everything has to be properly configured. Otherwise, nothing will work.
Yeah, it will take more time, sir. I would.
It will not compile itself.
Very true. Very true. See, that is the whole process. See, our intention is, for many of you people, for many of the new guys, they don't know how to read the VFP diagram. One is that. The second thing is, how do you see, this is the methodology, right? AUTOSAR talks about the methodology in which you have to work. You cannot directly code. So how do you follow the methodology? So you have to follow the ARXML method, right? What is ARXML creation? What is ARXML generation? What is RTE generation? So all those things has to be known, right?
Yeah, since they have restricted everything with the anything data exchange has to happen via RT only, so they have to follow that standard.
Exactly. And both your ASWC and BSW.
Sir, I have a question.
Please.
I have a question. We integrated BSW and ASW here. So the integration is basically calling the ASW and BSW APIs together or something. I didn't understand.
See, look at this. We generated the BSW and ASW, right? First, we independently generated that, and we saw that there was no compilation errors. After that, we started calling this. See, in the IO abstraction layer is the one in which actually you are calling the BSW function. Look at this. This is a BSW function.
Yes.
See, this function is calling this. Okay, I'll just open only those two files, then you'll understand. See, look at this. This is your ASWC. This function is calling the BSWC function, which is there in gen di and do. So this is the one which is reading the data from this function. This is the di. Okay, so there are no errors. There is some tool error. It will remove all the So now you look at it, all errors will go. So it is this function is calling a function which is there within this function. This is ASWC, this is BSW. From here, this function is going to be called.
Okay.
Now,
so we are
when
calling
this
this
function
integration.
is calling, right? This will not directly go to this ASWC functions. It is going to go to RTE only. Look at this. This is going to be called from an RTE function. This function will be called by an RTE only. Data exchange has to happen in RTE, right? How is it happening means I'll show you all the functions there. .h files, if you look at it. So this is your this is your value. How it is going to set. Yeah, these are the variables. If you look at it, the RT creates all the variables required. If you look at this, not this one, sorry. See, when a data comes here and if it is put here, no, this variable, this is a variable. Okay, this variable is going to be part of this RT. And that variable will be called as this.
Okay.
RTE instance SWC sensor digital 1. This is the variable name. And this will be done only in the RTE.h file. These are the global variables. If you look at it, these are the global variables, but it will be handled only by RT. If the value of the switch changes, no, nobody can make the change directly here. You cannot change it. It has to be changed only in the RTE layer. Who is going to change it? That will be done only by this guy, because this guy is a reader. He cannot change it. This guy is the writer. So this guy can change the value of LED. A variable is there. If the value of the variable has to be changed, only this guy can. That is the rule. Anybody else can read it, but only this guy will change.
Okay.
So that is the whole understanding. If you deal with RTE, all variables will be like RTE is the boss. All variables will be with RTE. You take it from RTE only. Okay. If you want to change anything, change it and put it back to RTE. Somebody else will take it.
Okay. So we are calling this integration of ASW and BSW.
Yes. The same thing, like very easily you can integrate. Okay. So CAN integration is little tougher, but our tool makes it very simple. So all you have to do is come here, enable the DBC. It will generate the CAN ARXML also. It will generate. So I'll just go and select the DBC. I'll make it very quick. So select this. Then add the CAN messages. The same way I'll add those two just to be very. Now, maybe what I'll do is in this, I'll send the output value. Sorry, the input value. Digital channel 1 is the only sensor I have. So this is transmission. So I'm going to transmit whenever the switch is pressed, I'll be sending in this message. So the moment I generate this, note that I have only one file now. CAN system ARXML is not there. I'll close this. I'll come here. I'll click on this, generate the ARXML, click on this. Now there are two ARXMLs. It has generated the CAN system ARXML also. This is little complex, but it generates all the things. Based on the 2 frames, I selected 2 messages. It has generated that, and the signals, all the signals whichever I wanted, it has selected that. It has selected the PDUs and all the positions, mapping, everything will come here. So you can go and look into this also. If I refresh this, it would have the file would have come here. The CAN system ARXML is available here. Yeah, you can see this in RTOP also. So it will tell you the position. This is where the position is. Everything will be automatically mapped by the tool itself. So once this is done, so I'm going to import this into a project. What I'll do is I'll create a new project itself, maybe. Okay, I'll delete this. Too many projects open. New, sorry, not library. A new example project. So examples, library, yeah, 11. These are some documentation related errors. Come back here. Read to flash. Now I have to generate the ASWC to this folder. Okay. So I'll give this folder as the ASWC folder. Has generated the ARXML. Next, I have to generate the ASWC. Sorry, the .c.h files. See, browse. This is the location. Then come back and give the ARXML source folder, which is this. And I'm going to select the ARXML file. Then finish. So now it would have generated the ARXML file into this folder. I don't know why this keeps coming in between. So I'll refresh this folder. So the files are generated. Now, if you look at it, it would have generated more code for sending the data to COM also. The same application layer, if you look at it, if I change the VFB diagram, the VFB diagram, there will be one more port which is going to send the data to COM. One is sending to RTE, one is going to send to COM through RTE. Okay, so that is what it has created. So now I have to generate this one. 1 second. There are some minor bugs here, which will be fixed soon.
Sir, we have to fix the or operators below.
Yeah, or operator I have put it. That I have put it.
Okay. Okay.
So then I have to open this file. Then select, not this. I have to import the ARXML to this also. The ARX file I have to map it. Finish. Then if I click on this, you note that the CAN messages has also come in here now based on your configuration. This for only for transmission. It works for reception also. I've done only this one. So now I have to build. Let us see how many errors it generates. It may generate a few errors because there are some issues, minor issues which we have to resolve.
In this configuration, COM, PDR, CAN-IF is not required, sir? Or
no, see, that is what I was telling, right? In the moment you talk about ICC1 stack,
okay,
the complete BSW is a black box.
Okay.
The moment it becomes a black box, right? So you don't have to worry about CAN interface, PDU router, nothing is required.
Okay.
But Srinivasan, once we introduce diagnostics and this, right? In the next releases, you will have the CANF and the CAN TP coming in.
Exactly.
Okay.
Yeah,
We already
we are
have
adding that also.
We've not integrated it here. So we are in the process of testing it. Once it is integrated, it will be available in the next release.
PDR also.
PDR also. As of now, we're integrating CANF and TP. And then after that, we will take signal mapping and message mapping also into it using the PDO.
But COM also you are introducing or what?
Sorry?
COM module in service
COM
layer.
manager.
No. COM.
COM
Normal.
is already there, right? Only
COM is
can
already
handle
there.
this.
COM is already there. You can see that here.
This is the COM.
Okay.
COM is already there.
See, the
but in-
idea again, if I have to repeat it, you don't have to follow any of the AUTOSAR rules below ICC, the BSW.
Okay.
Right.
But
what
we
we're
want to
doing
follow
is-
it. We want to follow it because our idea is to that. But ICC1 doesn't recommend you to follow.
recommend you to do that. But then our statement is we want to go step by step. Yeah. Today, if you see in the market, there is no hands-on utility available for individuals or POC development. So we are now trying to launch a toolkit where people can start adopting AUTOSAR, and stage by stage in the next 1 year, we will bring in all the layers, and we will also try to upscale to an ICC3 stack, but it will be a step-by-step process.
Agreed.
Okay.
So there are
See, I mean, if I have all of that, selling that at this price from a business point. The idea is make AUTOSAR affordable for everyone.
include rt.h. Okay. So now, again, it has come now. So it is built. So the only thing is I have to rewrite the entire code for the use. For this case, what I'll do is I'll not worry about the LED part. I'll only transmit the data through CAN. Okay. So what I'll do is I'll read the data. I'll rewrite this. So this is the application, which this is a new project. That's why. So I'll write this with the client call.
See, along with the tool, we'll also be very soon launching use cases, so that it's not just the LED blink or the CANCOM. You will also be able to get some applications developed. So we are building more tutorials now on this to show more use cases based output.
So note here, what I'm doing is, in this case, I'm reading the data. I'm not giving it to the LED. I'm reading the data and I'm giving only to COM. Just to make sure that I'm only giving it to the COM. So it is giving it to the COM now. And yeah, so that's it. So it will take the data. It has taken the data and written onto the RTE. The application has read the RTE and it is giving to the COM. This is called COM sender. So that is done. So then what it has to do is, I have to write the IO abstraction, which is going to, I'll not write the LEDs. I'll write only this. This one has got read the debound status. IO abstraction, read so these are unused, let it be unused. So I have to go and call from main RT loop. Include the rt.h. Compile. Now I'll put the new project. This is 11. Debug. So I'll open the tool TS master, so whether I'm getting message. So if I run this, I should get both the messages, and both the messages are running now through AUTOSAR with all the CAN system, ARXML, everything. And let us pray. If I press the switch, yeah, I'm getting the message here. So this is generated every 20 milliseconds. Sorry, 2 milliseconds. So this message is coming every 2 milliseconds. And this is running through completely through AUTOSAR code, ICC1. So now the LED is not glowing because the LED is not connected. The moment I map the LEDs, so the LEDs will also start glowing. So the mapping is done here. LED actuator mapping I have to do. The same way, I have to map it here in the abstraction layer. So this you know, right? So I'll not worry about that. So if you have any questions, sorry, I have taken too much time. Please let me know if you have any questions.
First, we need a feedback from you guys saying as a training or a POC kit, do you think this is good to start on AUTOSAR for people to understand RT, ASW, for editing the ASW files, and then slowly move on in the learning curve? Because as of now, we've not found good hands-on tools available anywhere in the market, right? Too complicated terms, too complicated configurations for the market. They want to keep it difficult so that people find it. So we want to make it more easier, and that is our intent.
I think they will keep it difficult and complicated, as you mentioned, to make it dependent on them.
Correct.
Might be
So
that
we want to ease it out as much as possible. That is why Ancit is now stepping in very hard on this and saying we are launching world's first AUTOSAR training kit, and we will make AUTOSAR affordable for everybody. And slowly we will also make SDV affordable for everybody.
that is the latest which we are targeting, I think, from Ancit side.
So we are already building a lot of pipeline products. I don't know if you've seen the sum IP generator of Ancit, right, which is targeting that space. We are now building some SDV products in similar lines. We also intend to, we are generating the RT, ASWC, BSW. We also want to generate the test cases from the same tool, right? So do you see this useful? I mean, what we want is a feedback.
That will be my open question from my end. You can take it in both the way. It's like since the classic AUTOSAR is like has been to a good level stable and stabilized. At the same time, like this market is completely occupied with like vector or anything else. EB, like well established, the OEMs prefer. How the things will be like in your side to plan it to reach it from ICC1 to ICC3, so that until unless the OEM don't use it, it will be always like at lower level, not at the global level, what I feel. So I think
actually, I don't know if you're aware of the German universities out there. They themselves don't teach AUTOSAR because they don't have a stack.
Yeah, therefore the Germany, I think what I know like is like on the lighter side of the software. They are more on the hardware side. What I feel, what I know.
Right.
See, one thing is, if I have to add there, see, our idea is not to take this to a product, but the idea is to teach what is the methodology in which AUTOSAR can be learned or how it is designed. See, end of the day, you can take this ARXML and use your EB resource and build your product. But what happens is in many cases, if it takes 6 months, 1 year to make just an LED blink or send a CAN message, now 1 year license is gone, EB resource. Now, if you start with this, you see again, EB resource doesn't give you a license for testing on a board. If you train the license, if you has to be actual board, right? They don't give you a license for an actual board, right? So if it was for training, they give you only like virtual license, virtual ECU license. Now the problem is, if you until unless you can make the product work with an ICC1 stack, the moment you make it work with an ICC1 stack, the second phase can be you can take it to the ICC3 stack and make it work. That is for the production. I'm talking about training. Training, the biggest problem is we don't have the tools to train also. So to teach the methodology on how AUTOSAR is architected, what is the reason behind the architecture, why RTE becomes very critical, to explain these things, right? If you look at a RTE code of EB or vector, no, it's very difficult to understand for you. So we want to see whether that can be simplified. Am I making sense? Hello, am I audible?
Yeah, you're audible.
Yes, sir. Yes.
So
Hello.
yeah.
At the end of the day, the production, right? See, if I have to honestly tell, for production, you may have to go to vector and EB only. But for training and POCs,
Or for
definitely this is
POCs.
a, yeah.
Yep.
This will be a POCs, your pilot projects. This can be a very good tool where you can immediately go for a POC, and your ARXML, at least your application ARXML will be ready.
Okay. All right. So I think, yeah, if no further questions, then I think 1 hour meeting has become 2 hours. But thank you so much. We were, I mean, we had all the participants online. We didn't have a dropout. You were watching that as well. So
Will a recording
so
of
much.
this be available?
Yes, we can make the recording available. Yeah.
That will be available on the Ancit website, I think.
Right. Yeah. What we'll do is, at least to these participants, we'll write an email and circulate the link once
Yeah,
we
that will
upload it.
help. That will help. Thank you.
Yep. Yep. All right, then. Thank you so much. And feel free to reach out to any of us and write to us. We would be more than happy to help.
Thank you. Thank you for the
Thank you.
session.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.